Hello everyone. Today, we'll continue our discussion on reinforced concrete design. This is part 3 of the module, and our main focus will be on the design of T-beams. In our previous discussion on analysis, we emphasized the importance of determining the location of the neutral axis. It can either lie within the flange or extend into the web below the flange. The position of the neutral axis dictates the design process we follow. Now here are the steps we are going to follow. First, if it is not a given value, we compute the width of the flange using the provision of the code. Next, we solve for the equivalent depth of the compression block, A, and check if the value of A exceeds the thickness of the flange, or HF. If A is less than flange thickness, we will design the beam as a singly reinforced beam. But if A exceeds H or AF, the compression block will not simply be a rectangle, but a composite shape. The area of the overhang shall be isolated, and just like in a doubly reinforced beam, the increased compression would also allow us to increase the tension capacity. The tension reinforcement shall be made up of two sections, ASF and ASW, which correspond to the segments of the compression block. We will now discuss a design process you may follow. The steps are structured to be easily applied in hand calculations, spreadsheet templates, or programmatic implementations. Feel free to modify the process as needed, starting from the given values. We now assume the strain-based design classification and the reinforcement layout. Specifically, we will use the tension-controlled classification, which corresponds to a strength reduction factor of 0.90. Initially, we assume a single layer of reinforcing bars. Next, we use the provided flange width or compute the value using the NSCP C101 provision under section 406.3.2. We then compute a trial equivalent compression block depth using a derived formula as shown. The computed equivalent compression block depth is compared with the value of the depth of the slab or flange. If the block depth is less than the slab, the beam is designed as a regular SRRB. While if the block depth is greater than the slab, the beam is designed as a T-beam. We first compute for a portion of the area of reinforcement ASF that will compensate for the slab overhang using a derived formula as shown, followed by the computation of the portion of the capacity, Mn1. The other portion, Mu2, is computed by subtracting phi Mn1 from the ultimate external moment, followed by solving Rnw from Mu2 and ρw using the value of Rnw. ρw will be used to solve the portion of the reinforcement proportional to the compression resistant of the web block. The total area of reinforcement can now be solved by adding ASF and ASW. We'll have to solve the minimum required reinforcement using the same provision as rectangular beams, but with an additional provision from 409.6.1.2 for inverted T-beam, where the flange or slab is in the tension side. Moving forward, we compare the computed AS with the minimum required. If the computed is less than the minimum, we'll increase the value of AS, or just simply use the value of the minimum. But if the minimum value is exceeded, we solve for the new compression block depth AW using the value of ASW. We then solve for beta 1 using the code-based formula. This will be used to solve for the final compression block C, and the value of the steel strain ES can be solved using the derived formula of ES from the Whitney stress diagram. This can be used to check against the minimum requirement of the code for beams with axial stress less than 10% of Ag times Fc prime. If the value of the strain is less than 0.004, we'll have to redesign the beam section or material properties as it is not allowed by the code. If ES exceeds 0.004, we further compare it with 0.005 to verify if the initial assumption of tension, controlled section, is correct. While if ES is less than 0.005, then we'll have to decide if we'll retain the section size and choose to add compression reinforcement, making the section doubly reinforced, or choose to redesign the beam section or material properties. Either way, we'll have to redo the entire calculation to accommodate such changes. If ES exceeds both 0.004 and 0.005, we can further check the rebar spacing. If the rebar spacing is not satisfactory, then we'll have to change the assumed bar layers and redo the calculations. If all checks are passing, we are now ready to do the detailing. Notice that for every redesign, the flowchart leads to step C. It is basically a call for an iterative process where we will go back to the initial assumption we did. From there, we repeat the entire calculations. Now, just a quick reminder, the steps I've shown you here are simply prescriptive, meaning they're meant to guide you through the process, but they're by no means set in stone. If along the way you find a better approach, or if there's something you think can be improved or made more efficient, by all means, go ahead and make those changes. Don't feel like you have to follow this exactly. Use your own judgment to make it work best following the provision of the code. Now, to better understand the concept, we will be having an example. Let me read the problem statement for you. Determine the required reinforcement for the interior beam shown below for a positive factored bending moment, which is equal to 300 kilonewton meters. Assume that the specified compressive strength is 28 megapascals, a 20 millimeters maximum aggregate size, and grade 420 reinforcement. The beams are spaced 1,500 millimeters on center, and the clear span is equal to 7 meters. From the statement of the problem, the value of the width of the web is equal to 300 millimeters. The width of the flange is 1,500 millimeters. This value can be revised using the provision of the code, or we can just retain this value as is. For this problem, we are going to recompute the value of the width of the flange. The height of the slab is 150 millimeters. The total beam height is 600 millimeters. The specified compressive strength is 28 megapascals. The yield strength of the steel reinforcement can be inferred as 420 megapascals. The given ultimate moment is 300 kilonewton meters. And the clear beam span is 7 meters. We can then solve the clear spacing between each beams by subtracting half of the width of both adjacent beams from the center to center spacing between the beams. Let us solve the problem. Let us first declare our assumptions: tension, controlled section, and single layer reinforcements. We will ignore the value of the given flange width and solve the effective value using NSCP C101 provision under section 406.3.2. Note that, as per illustration, the beam is both ends continuous. We solve the value of beta 1 as per code. And from the assumption of single layer reinforcement, we solve for the value of the effective depth. Next, we solve for the value A sub 1. This will be used to compute for the initial value of the equivalent compression block A. Using the derived formula for A, the value will be as follows. We can now check if the value of A exceeds the thickness of the slab HF. Since A is inside HF, the section can be designed as SRB. So Rn can be directly solved using the value of Mu. Take note that the width to be used will be the value of the computed effective width of the flange. The value of Rn can be used directly to solve for the value of the steel ratio of the beam. And using the value of the steel ratio, the steel area can be computed as follows. From the value of As, we can solve for the value of A. We convert the value of A into C by dividing it with the value of beta 1. From the value of C, we can now solve for the value of the steel strain. And finally, we can compare the value of the steel strain with 0.004 as per code requirement and 0.005 to check if the initial assumption of tension controlled section is correct. Let us now check for the value of the minimum steel reinforcement using the provision of the code. The computed value of the steel reinforcement is greater than the minimum, therefore we can now proceed with the next step. Let us compute the value of numbers of bars using the computed value of AS. Once we've completed the calculations and confirmed that everything checks out, the next step is to move on to the detailing. This is where we translate all those numbers into a visual representation by drawing the actual beam details, the dimensions, reinforcement layout, bar sizes, spacing, and everything else needed for construction or documentation. At this point, we can go a step further and check the spacing of the reinforcement. Now, you've got a couple of options here. You can either directly compare the actual bar spacings with the allowable limits, or you can calculate the minimum and maximum number of bars that can fit per layer based on code requirements. Either approach is perfectly valid, so feel free to use whichever method you're more comfortable with, or whichever makes more sense for your design process. Alright, so what we're going to do now in the next example is go back and redo the same problem, same setup, same conditions, but with one key difference. This time, we're going to increase the external load and bump it up to 2800 kilonewton meters. Let's see how that change affects the design and walk through the entire process again with this updated load. We're working with the same given values as before, except for one change: the external load. Everything else stays the same. The assumptions we made earlier, the calculated effective flange width, the value of beta 1, and the effective depth, all of those remain unchanged. So we're essentially just updating the load and seeing how that affects our design. With the updated value of mu, we are required to recompute the value of equivalent compression block depth using the derived formula. With the new value of the equivalent compression block, we can now check if the beam behaves like a rectangular beam or a T-beam all the way. The compression block depth exceeds the slab thickness. We'll design the beam knowing that the compression block is not just a rectangle. We solve for ASF using the overhang as the compression block. From the value of ASF, we solve for the value of the portion of the capacity, phi-mn1. We subtract the value of phi-mn1 from the ultimate external moment to get the value of mu2. We'll use the value of mn2 to solve for the value of rnw and subsequently to solve for the value of ρw. In this example, the value of ρ is an imaginary number. This means that the value of the external load exceeds the maximum moment that would allow it to be classified as a singly reinforced beam. Therefore, we'll have to stop the calculation here and declare that this beam should be designed as a doubly reinforced. We will not proceed further with the design iteration of this problem and move forward to the next example. In this next example, let us design the same beam in example number 1, but this time we'll increase the load such that the strain of the steel will be less than the requirement of the code. Just like in example number 2, there will be no changes to the calculated values of the effective width of the flange, beta 1, and the calculated effective depth of the beam. Let's just skip this part and move on to next step. Alright, so in this step, we will start by solving for the initial value of the equivalent compression block depth, denoted as A, using the increased value of the external moment, that is mu. Once we have that, we'll compare the value of A with the thickness of the slab to check whether it's still within the flange or not. Just like in example 2, we'll likely find that A exceeds the slab thickness. If that's the case, we'll move forward and calculate the portion of the steel reinforcement force acting within the slab overhang. That's what we call ASF. Then we'll use ASF to compute the nominal moment capacity from the flange portion, which we'll denote as phi-mn1. After that, we'll subtract phi-mn1 from mu to get the remaining moment, mu2. Finally, we'll take that mu2 and use it to solve for rnw, which is the concrete beam design ratio for the web portion of the section. Next, we will solve for the value of ρw, which is the steel ratio for the web, using the value of rnw that we previously calculated. Once we have ρw, we'll use it to determine ASW, the area of steel required for the web portion of the section. Now, keep in mind that the total area of steel, AS, will be the sum of ASF, which came from the slab overhang, and ASW from the web. With that total steel area, we'll then compute the minimum required steel reinforcement as per code and compare it to our calculated AS. If the computed steel area turns out to be less than the minimum required, we will use the minimum value instead, since that's what the code requires for ductility and structural safety. After finalizing ASW, we'll move on to solving for the new value of the equivalent compression block depth, which we'll now refer to as AW based on the updated reinforcement. This AW value will then be used to solve for the final compression block depth C in the concrete. And finally, with the value of C, we'll proceed to solve for the strain in the steel reinforcement, a key step in verifying whether the section behaves in a tension-controlled manner. In this example, we will find that the computed strain in the steel is actually less than 0.004. Now, based on code requirements, particularly for a tension-controlled section, and since there are no given external axial load, This means the section does not satisfy the minimum provision. At this point, we would typically explore a few possible options. We could choose to redesign the section as a doubly reinforced beam. We could increase the size of the cross section to improve capacity, or we might adjust the material properties, for example, by using a higher grade of steel or concrete. However, for the purpose of this discussion or example, we won't go into the detailed recalculations for those alternatives. We'll stop the computation here, but just keep in mind that this design, as it currently stands, would not be acceptable under standard code provisions. Alright, let's move on and try another example, but this time we'll use a different value for the ultimate moment. Specifically, we'll select an MU that's expected to produce a satisfactory steel strain, meaning a value that meets the tension-controlled criteria set by the code. With this adjustment, we should be able to walk through the design process and arrive at a result that fully satisfies the strength and ductility requirements. Let's see how it plays out. Just like in the previous examples, we won't be making any changes to the previously calculated values. That includes the effective flange width, the value of beta 1, and the effective depth of the beam. Since those parameters remain exactly the same, we'll go ahead and skip the recalculations for this part and move straight into the next step. The same pattern, we will start by solving for the initial value of the equivalent compression block depth, denoted as A, using the increased value of the external moment, that is MU. Once we have that, we'll compare the value of A with the thickness of the slab to check whether it's still within the flange or not. Just like in example 2 and 3, we'll likely find that A exceeds the slab thickness. If that's the case, we'll move forward and calculate the portion of the steel reinforcement force acting within the slab overhang. That's what we call ASF. Then, we'll use ASF to compute the nominal moment capacity from the flange portion, which we'll denote as phi mn1. After that, we'll subtract phi mn1 from mu to get the remaining moment, mu2. Finally, we'll take that mu2 and use it to solve for R&W, which is the concrete beam design ratio for the web portion of the section. Next, we will solve for the value of ρw, which is the steel ratio for the web, using the value of R&W that we previously calculated. Once we have ρw, we'll use it to determine ASW, the area of steel required for the web portion of the section. The total area of steel AS will be the sum of ASF, which came from the slab overhang, and ASW from the web. With that total steel area, we'll then compute the minimum required steel reinforcement as per code and compare it to our calculated AS. If the computed steel area turns out to be less than the minimum required, we will use the minimum value instead. We'll move on to solving for the new value of the equivalent compression block depth, AW, based on the updated reinforcement. This new equivalent compression block depth value will then be used to solve for the final compression block depth, C, in the concrete. And finally, with the value of C, we'll proceed to solve for the strain in the steel reinforcement. The strain of steel turns out to be greater than 0.004, which satisfies the minimum provision of the code. This means that we can proceed on to the next steps. Now, from the value of AS that we've just determined, we'll go ahead and solve for the required number of reinforcing bars. Once we have that, we'll compare the result against the code, specified limits for minimum and maximum bar spacing, just to make sure everything fits within acceptable parameters. In this case, our calculation shows that we need a total of 42 bars, and even without doing a detailed spacing check, it'll be quite clear that this number simply won't fit within the width of the beam if we try to place them all in a single layer. That tells us right away that our initial assumption, using just one layer of reinforcement, is no longer workable. Ideally, at this point, we would revisit the design and make some adjustments. That could mean switching to a 2 or more layers of arrangement, increasing the beam width, or exploring alternate bar sizes. However, for the purposes of this example, we won't go any further into that redesign. We'll stop the process here. And that wraps up our discussion for this video. I hope this walkthrough helped clarify the key concepts and steps involved in reinforced concrete T-beam design. If you found this lecture helpful, feel free to check out the other videos. Don't forget to like, subscribe, or share. And if you have any questions or suggestions for future topics, feel free to leave a comment below. Thanks for watching, and I'll see you in the next one.